Hello everybody, and welcome back. Think you know what the strongest material is? You might be surprised to learn that the answer depends not only on the substance, but on the way atoms are bonded. In this video, we are going to delve into the different networks that make up compounds, including ionic networks, covalent lattices, and covalent molecular networks, and metallic structures. And to top it all off, I'll give you a secret hack in order to determine what type of bond is occurring between a compound. Pretty handy, huh? This video is going to be your best place to start if you want to ace Year 11 chemistry. My name is Will, and I'll be your online chemistry teacher today. So without further ado, let's get into it. The first type of atomic network you have to be familiar with is the ionic network. The ionic network consists of a giant lattice filled with negatively charged anions and positively charged cations, held together with electrostatic force. They are formed through ionic bonding, which, don't worry, we'll touch more on that later. If you look at the diagram, you can see there seems to be sticks connecting each ion. Do not let this confuse you, as they are not actual sticks holding together lattices, but it is just a representation of electron clouds. Ionic networks are three-dimensional, highly ordered arrangements of electrons that span almost endlessly in a pattern. Ionic networks can form crystalline and amorphous structures depending on the conditions the solid formed under. Usually it will form crystalline structures if this process is not rushed, and vice versa for amorphous. Now let's examine the properties of ionic networks. High melting and boiling points. Ionic networks have such a strong bond because of their electrostatic attraction between ions. It requires a lot of energy to melt or boil an ionic solid. Next, they are hard and brittle. Though they are hard, also because of the strong electrostatic forces, they are very brittle. If you can imagine the lattice for sodium chloride, you can see that if we smash it with a hammer, all the ions would shift down one and repel each other due to them having the same charge. This is why ionic networks are not malleable but instead shatter. And finally, they are poor electrical and thermal conductors when solid. Ionic networks are poor electrical conductors because the electrons are locked up in bonds, and as we know, electrons are negatively charged and therefore conduct electricity when free to move around. So in solid form, ionic networks will not conduct electricity, but if melted to become a liquid form or dissolved in a solvent, the ions are able to move freely, therefore making them good conductors. Now, it's time to look at covalent networks. These can form crystalline and amorphous structures, amorphous networks, just like ionic networks. The most important thing to understand with covalent networks is that there are two types, covalent lattices and covalent molecular networks. Two prominent examples of covalent lattices are diamond and silicon, as you can see in those pictures there. In silicon dioxide, each silicon atom forms 4 covalent bonds with 4 oxygen atoms. In silicon dioxide, each silicon atom shares electrons with 4 oxygen atoms. This means that each silicon forms a single covalent bond with 4 oxygen atoms. The majority of sand on beaches is actually made up of silicon dioxide. In diamond, each carbon atom forms 4 covalent bonds with other carbon atoms. This means that each carbon atom forms a single covalent bond with 4 other carbon atoms. Each covalent bond is very strong. Diamond is a very hard substance due to the strong covalent bonds, and it means that diamond is very difficult to break. Diamond is actually known to be one of the hardest naturally occurring substances found on Earth. Diamond and silicon have a similar property due to their similar structure. The covalent network of silicon dioxide forms a tetrahedral lattice, and the covalent network in diamond also forms a tetrahedral lattice. Now it's time for some properties of diamond and silicon dioxide. Hard but brittle. Diamond and silicon dioxide are incredibly hard due to the strong covalent bonds, but as a result of this, they are also incredibly brittle as their covalent bonds are stiff, which leave no room for malleability, which in turn shatters the covalent lattice if enough force is applied to a certain area. High melting and boiling point. The many covalent bonds in silicon dioxide and diamond are very strong. Therefore, a large amount of energy is needed to break, and a high temperature is required. They do not conduct electricity in their solid or liquid form. Diamond and silicon dioxide don't conduct electricity because all their electrons are involved in strong covalent bonds, leaving no free electrons to carry, a charge in contrast to compounds like salts or metals. Let's move on to covalent molecular networks. Covalent molecular networks are the second type of covalent networks. Covalent molecular networks are things like water, which is still particles. It was still individual molecules held together by intermolecular forces. The intermolecular forces that hold together covalent molecular bonds are weak because they arise from temporary interactions between molecules, unlike the strong intramolecular forces like covalent bonds that hold atoms together within a molecule. Now, these two words might sound the same, but they are actually very different. Intramolecular forces, like covalent bonds, are the strong forces that hold atoms together within a molecule. Intermolecular forces are weaker forces that exist between molecules, arising from temporary charge distributions or dipoles. Properties of covalent molecular network solids are low melting and boiling points. The weak intermolecular bonds can be easily broken down by heat. Poor conductors of electricity. This is due to the fact that there are no free electrons in their structure. Soft and brittle, due to the molecules being able to move around. Now it's time for a final type of network, metallic structures. Metallic structures are tightly packed lattice structures. Metallic structure is a result of metallic bonding, which is simply the way two metals bond together. It is a process where metal atoms share all of their valence electrons in a sea of delocalized electrons, forming a strong electrostatic attraction between positive metal ions and the sea of delocalized electrons. The delocalized electrons form the glue that holds the positive metal ions together due to their different electrostatic charge. Metallic bonding can take place between the same metals, forming a pure metal, or different metals forming an alloy. When a pure metal is formed, the metallic bonds occur between atoms of the same metal. For example, a piece of aluminium foil or a copper wire are examples of pure metals held together by metallic bonds. When two or more different metals combine, they form an alloy, which is still held together by metallic bonds. Examples of alloys include brass, which is copper and zinc, or white gold, gold and other metals. Now finally, the properties of metallic structure. They are very good thermal and electrical conductors. This is due to the sea of delocalized electrons that freely move around. They have a high melting and boiling point due to strong metallic bonds. They are malleable. Metallic structures are not rigid in the way ionic and covalent networks are because of the fact that the sea of delocalized electrons in a metallic bond are able to shift as they are not bound to a single bond between two atoms. This is why if you smashed metal with a hammer, it would not shatter. It would just reshape itself, sort of. They are good electrical conductors in solid and molten form. This is due to the sea of delocalized electrons being free to move around because they are not rigidly bound to a single bond. Now, for a brief investigation into the difference between ionic and covalent bonds. An ionic compound is a chemical compound formed by the electrostatic attraction between oppositely charged ions. A covalent compound is a molecule formed when two or more non-metal atoms share electrons to form a chemical bond, resulting in a neutral, stable molecule. Now, time to switch it up a bit. Let's define electronegativity. Electronegativity is of paramount importance because it can help us determine the type of bond in a compound. Electronegativity is the chemical property that describes an atom's ability to attract electrons towards itself. Typically, if the electronegativity difference is greater than 1.5, it's an ionic bond. If it's less, it is a covalent bond. Also note that ionic bonds are much stronger than covalent bonds because their electronegativity difference is so large, and as we know, opposites attract. This is why typically elements from opposite ends of the periodic table bond so strongly. This is an example of a covalent bond using the Lewis dot structure. You can see this because the oxygen, nitrogen, and chloride atoms are sharing electrons instead of completely transferring them. This is an example of an ionic bond using a Lewis dot structure. You can see this because the atoms are transferring electrons to each other instead of just sharing them. I hope you learned something today. I certainly did. And I hope you can take away a lot about atomic networks and the difference between ionic and covalent bonds. Thank you for listening.